Are there any questions so far? Good. Everybody having fun? No, don't answer that. Anyways, what the heck? How come I can't see? Nobody wants to talk. Go ahead, Mike. Come on. I'm going to have to shut this off if this continues. All right. If anybody have any, if there are any questions, please put up your hand, say something. Otherwise, I'm going to continue. We do have, about 5 lectures left. 1, 2, 3, 4, 5, 6. We can do it. Oh, that's the other thing that I did forget to mention. The 2-hour exam is probably going to be, or 2-hour quiz, sorry, is probably going to be ready by Friday. Monday, it'll probably be given Monday after class, most likely. So I'll let you know about that. And yeah, that's about it. If there are any more updates or whatever, I'll let you know. Let's begin. Like I mentioned, we've got about six lectures. We will be done for sure by Monday, and probably have enough time to cover some other stuff. Yes, Mike. Okay, can you chat? Oh. Ah.
There we go.
Wonderful. Thank you very much.
Chat muted.
Okay, good. You know what? That is another bug with Moodle, unfortunately. You have to redo this every single bloody time, which is so annoying. But whatever. Okay, good. We got it. I'm assuming everybody did hear what I was saying before, or no? Can somebody please answer by unmuting their mic?
Yeah, we heard it.
Okay, good. All right. Geez. Already I feel like just throwing in the towel and watching YouTube videos and saying, let's write this one off. But luckily, we're all professionals, and that's not going to happen. So let's get back to work. You guys have been listening to me for quite a while, so let's watch a video right now. I'm assuming, I don't know if David has shown you this before. Back in the late 90s, early 2000s, and probably even up to now, there used to be a lot of people, well, some people scamming going around. Okay, so my screen is not shared. Ah, bloody heck. Okay, it's anyways, the now my my screen shared. You know what? I'm going to whose brilliant idea was it to have the lab section in this lecture? Because I blame that person. Don't take credit for it. It was a good idea. So everybody can oh, Nicholas, you're not my favorite anymore. Um yeah, because of course didn't go through the normal checklist. Thought, hey, everything should work. All right. So anyways, David may have mentioned before about this scam going around. It was popular in the early, late 90s, early 2000s, and possibly now. So this kind of explains it, and you should be aware of it, and let other people know or whatever.
We're doing a demonstration of the common scam of what the precipitator does, that it shows that there's dirt in the water. Here we have 2 cups of reverse osmosis water, which aren't conducting any electricity. Here we have a precipitator, which is often used to sell RO systems and to sell reverse osmosis water. What it does is it basically puts main current through a copper electrode and an aluminium electrode. Then if the water conducts electricity, say if there's salt in the water, then the copper and aluminium exchanges, and that causes the water to change color. Now, to demonstrate, we'll put the precipitator on here for about 2 minutes. In water that doesn't conduct any electricity. As you can see, there's nothing really happening. It's just standing in water. I don't think there's any point keeping it longer than that. Nothing happening. Just turn that off. Then we'll take just a pinch of table salt, which is perfectly healthy, nothing wrong with that. Put that into the water. Just give it a bit of a stir. TDS reading again. Okay, so got a bit of minerals from the electrodes there. Is this side? Okay, hold on. Oh, okay, it seems to have a lot of minerals in it. Doesn't want to cooperate. It turns off if I put it in there. But the result is, we put this little machine in here now. And there you can see it's immediately reacting, and ion exchange is taking place. That's changing the color of the water and creating the perception that the water is contaminated and dirty, which in fact isn't true, because as we've just shown, that is simply a result of the water conducting electricity, which we created by adding salt.
Right. So all the color was obviously the ions oxidizing off the iron rod inside the water. Incidentally, can somebody put up their hand if you'd seen this before? Riveting stuff, whatever. Okay, so yeah, and this was a common scam that went around for quite a while. But let's finish this lecture. I had done a really quick and dirty review before. I'll redo it. We had talked about conductivity probes, just basically what it is. Went into how it operates, the 2-cell type, the 4-cell conductivity probes, and then we talked about the toroidal conductivity probes, how similar it was to the meg meter. So it's, I mean, it's the exact same principle, except instead of having voltage pickups, you've got another coil here that will pick up the induced current. Yeah, so and you may see these in industry, so you can at least recognize them. The one thing about these is you do need flow, constant flow, whereas this kind, the probe type can just sit in the water. Yeah. All right, so now we're talking about TSS. So obviously, total suspended solids are particles in water that are larger than 2 microns. So anything smaller than 2 microns, and that's my own definition. David may have his own definition. Is considered a dissolved solid. So know where this information is, because something like this is will most likely show up on the exam. Obviously, most suspended solids are made up of inorganic materials, algae and whatnot, and they also contribute to TSS. Oh, if I'm going too fast, I can't remember. I don't have my book in front of me, so just let me know if there are blanks or if I'm going too fast. So we quite often in the water industry use turbidity to give us an idea of the total suspended solids, but of course that is not accurate, and we need other instruments that give us that capability. So we know the definition of turbidity. Usually for a nephelometer, it is measuring the scattering of light, and generally at 90 degrees. Although there's new technology for the 360, and I'll show a video about this. Will be one of the introductions to the labs that I'll be discussing later. The hack 360 degree, which is an unproven technology right now. Some debate about it. But suspended solids, of course, are the total of everything: the organics, inorganics, riverbed, etc. So usually, most of the time, it's they're measured in milligrams per liter, and the most accurate method of determining it, TSS, is of course in the laboratory. You have to filter, dry it out, and weigh it. That's the only accurate way, really, to measure TSS. So the two main ways we measure total suspended solids is gravimetric methods, and of course conductivity. So gravimetric laboratory, it takes too long. We need the quick and dirty method. So but conductivity probes do not give the full picture. So newer TSS instruments, they use light emitters and detectors, and they're arranged in a 360-degree method. I'll be showing a video in just a bit about the new ones. Can I go back to this one here, Megan? By the way, Richard, nice comment. Unfortunately, well, actually, you know what? I bet a lot of people still buy into that scan. Oh, okay, Megan, thanks. All right. Right. So we'll watch a video in just a second. Oh, I'm not sure. Unfortunately, this video here that we used to watch died on me, and I'm not sure about this video here. We'll see if it's the one that explains the principle, one that I want.
Controlling turbidity and suspended solids levels in treated wastewater discharged to the environment is vital to ensuring the health of rivers and streams and preventing damage caused by depletion of dissolved oxygen levels. For this reason, turbidity and suspended solids concentrations of effluent discharges are tightly regulated and need to be carefully monitored to ensure limits are maintained. In municipal wastewater applications, excessive suspended solids levels can trigger a chain of events that can steadily deplete the level of oxygen in the water needed for a healthy aquatic ecosystem. As particles build up, they scatter the daylight passing through the water, reducing its strength. With less direct light for effective photosynthesis, aquatic plants struggle to produce the oxygen needed for the survival of other aquatic life, including fish, amphibians, and waterborne insects. Within the wastewater treatment plant itself, excess turbidity can be indicative of a poorly operating treatment process. It is important to address this issue as residual suspended solids breaking through from sewage digestion processes will continue to have a biological oxygen demand as they enter the receiving water. Controlling suspended solids is equally important in industrial wastewater applications, where there is the added risk of toxic or metallic compounds escaping into the environment. Expressed in nephelometric turbidity units, NTU, turbidity measurement enables the level of suspended solids present in water to be accurately assessed. ABB's ATS-430 uses internationally approved nephelometric measurement technology to accurately measure turbidity concentrations up to 4,000 NTU. The sensor directs a beam of infrared light into the sample. The light beam is scattered by particles in the sample, and the scattered light intensity is measured by the sensor's photodetector positioned at 90 degrees to the light beam. The scattered light detected by the sensor is directly proportional to the turbidity of the sample.
So I'd like to add that this this kind of method is quite often used in wastewater treatment facilities. So, for instance, in the effluent coming out. You want to obviously measure the turbidity, and if you, rather than have a wall-mounted unit, you just have to have this kind of setup, just like, just basically a pulse inside the ground. And you will see them when we go back, or when you go to a wastewater treatment facility, you'll see rods sticking into the effluent. And every once in a while, you'll see a little air bubble coming off, and that's just a jet of air, just to clean off the residue or whatever on the lens.
Light beam. The scattered light detected by the sensor is directly proportional to the turbidity of the sample. Analysis of the signal conditioning is conducted within the robust sensor housing and transmitted digitally to the transmitter. The turbidity measurement can be used to determine the total suspended solids, or TSS, of the sample by comparison to laboratory data. The ATS-430's adaptive TSS calibration feature enables the sensor to intelligently calculate the TSS conversion based on historical process data. This feature provides a smooth TSS conversion and avoids sudden changes in TSS calibration coefficients, often caused by non-representative sampling or erroneous lab results. Setting up the transmitter and sensor is easy. Each sensor is precisely calibrated at the factory, so it is ready to use straight out of the box. Simply connect the sensor using ABB's EasyLink connection, and the transmitter will automatically configure the sensor setup. The Aztec AWT440 universal transmitter can be connected to up to 4 Aztec 400 digital sensors.
All right, so obviously, oh, okay, we might be getting into some of the specifics. I'll just have to give a very quick breakdown rather than listen to their spiel. Although ABB does make half decent equipment. It's worth watch. If once you get out into the into your specific plant, wherever you end up, watch their promotional videos, and obviously, you know, read their manuals just to get an idea. If you end up in a, let's say, a water or wastewater treatment plant, and there's a new piece of equipment that's turned out, a good recommendation is become the expert on that piece of equipment. You know, seriously, study everything on it, and be that the go-to person. Oh, well, yeah, you know, Nick, he knows that instrument. Go ask him, or that pump, or whatever. Or yeah, Megan, she knows that process. Go ask her, because that way you sort of become invaluable. You're invaluable because obviously you've got the schooling and training and stuff, but you're that much more valuable. All right. Anyways, enough about that. One thing that we're going to talk about too is our particle streaming counters. But I'm going to leave that in a second. Aaron, did you want to chat it out or just use your mic? Nope. Got hands down now? Okay, good. All right, let's go on to the next one, next lecture. I really debated doing this one today, but I think we can do a very quick and dirty lecture on this. You guys should know pH really well. It seems to be one of David's favorite topics. Actually, I want everybody to try to get all the labs in by, yeah, within 2 weeks. Now, there's no requirement, or I can't require it because I did say in the or it does say in the course outline that the classes end on the 10th. But it's in your best interest to have them handed in right away, just so you know where you stand. Of course, you still need 50% of the mark, or 50% to pass the lab. But no, it's not a requirement. It's better if you do it as soon as you can. Yeah, the final quiz is going to cover everything. Think of it as a practice for the final exam. In fact, it will basically be the final exam, just not officially. Yes, I already mentioned that. I'm going to, why don't we just take a 10-minute break? It's probably for the best. And just ask questions and stuff. So just, or how about 5 minutes? Because the time. But yeah, if you have any questions, why not unmute your mic and ask so everybody knows, or whatever. Or don't. I'm going to mute my mic. Go get a cup of coffee. Yes, we will have Yes, we will probably have 2 more quizzes. There's going to be one on Sunday on everything that we've covered up till the midterm, and then the big 2-hour quiz. Alrighty. Nick, I was tempted to click on that link, but unfortunately there are video nasties out there. So yeah, you never know. Okay, guys, it's been 5 minutes. Yeah, it's true. The I did like the comments about the the oh darn, where is it? Sunday union rules. Not very. Oh, there it is. It's not very union. Unfortunately, union rules are out the window right now due to COVID-19. So yeah, that's the way it is. Seriously though, the quiz will be open for a day or something because it's outside. Probably 2 days. And same with the 2 hour quiz. Of course, the final exam, when it is set, it will be set for that exact time. But it will be online and probably open book. Okay, so let's get to pH measurement. I really debated whether or not to do this one today. Again, and I apologize. This is the one thing I didn't grab from the college was the course package. So I don't remember how many blanks there are on this, and a lot of this is just the background of pH, which you should know by now through, of course, both chemistry and biology and David's class. Still, I have to cover it for the instrumentation part. So I'm hoping to go quickly, but if I go too quickly, start raising your hand right away, please. Okay, so obviously, okay, and I do have to do this to see. Oh, okay. If somebody raises their hand. Welcome, Tej. If hopefully you can hear. If you can't, please just maybe get some help. Text somebody. All right. So obviously, pH is vital for life. So for instance, blood must be between 7.35 and 7.45 pH. Now that's very, very limited range, of course. And pH is necessary for coagulation, flocculation, and if you ask David everything else, if there's a problem, blame it on pH. If you can't blame it on pH, just tell them it's that transducer acting up and you'll get to it right away. Don't do that, of course. We're always joking, but yeah, you can blame a lot of stuff on those two things. So obviously, water does dissociate naturally, but it does in a very limited, small manner. Water is actually a very stable molecule. So pH of water is basically zero. Sorry, 7. So it's neutral. pH, you guys know, describes whether something is acid or basic. It's measured generally on a scale of 0 to 14, although you can exceed these ranges in specific circumstances. And pH is equal to the negative log of the hydrogen, number of hydrogen ions. So luckily, we will not be doing any math regarding this. I used to. I don't know why, but we won't be. I don't know if there's any blanks on this. I basically mentioned this before. The next tables just give an idea of the amount of ions for each number and stuff like that. But just you guys know already, 7 is neutral. If it's less than 7, it's acidic. Greater than 7, it's basic. So there's the concentrations. Again, you don't have to know this for this course. You guys should know it for obviously the other courses. Everybody should know what an ion is, and obviously if an atom or a molecule gains or loses an electron, they become ions. So this just gives a nice idea of the basic level of acidic acid or basic. So vinegar right now, our vinegar is about 2, and that's what we use in the lab. Lye is around 12, so it's close to bleach, and that's also what we use in the one lab. Obviously, addition of acid to water makes it more acidic. Adding a base to water makes it more basic. I'm not going to go into the hydroxyl ions and all this. You should know that in the chemistry. Am I going too fast, by the way? If I am, please somebody put up their hand. Good. I'm assuming everybody knows this. That's why I'm kind of breezing through it. Acids are proton donors. Bases are proton acceptors. Oh, and by the way, even though I'm breezing over this or I'm going quickly, because I'm assuming everybody knows this already, this is still fair game on the exam. So know where this is. Obviously, it's going to be in pH. All right, I'm not going to do this. This won't be on the exam. This is chemistry. So how to measure pH? There are quite a few ways that is done in the industry. The most common way, though, involves the use of a pH-sensitive glass, so it allows ions to pass through, and having a reference electrode. So basically, pH measurement system, what it has is an electrode that measures the concentration of hydrogen or hydroxyl ions in a solution that dissociate through a permeable glass bulb. So the holes in this glass bulb are small enough to allow hydrogen ions to pass through, and that will cause a reaction inside the solution, which creates a millivoltage. And this millivoltage is then compared to another reference electrode. So this reference electrode is sitting in a solution, and it generates a certain voltage constantly. And so the measuring electrode will either generate, based on the number of hydrogen or lack of hydrogen ions, a higher or a lower voltage than the reference electrode. So that's the basic premise behind how a pH, electronic pH system works. Does somebody want me to try to explain it in a different way, or does everybody have the basic concept of how this works? If you do, please put up your hand. No, don't be embarrassed. Or be brave and put up your hand if you want to hear it another way. Okay, so in that case, I think that this is a fair. Thanks, Quinn. Please continue speaking for the group. I'm sure everybody appreciates it. So, and I'm joking there, by the way. You're my favorite. So, okay, you're not speaking for the group anymore. So, this will be one of those questions on a final exam. You know, for five marks, explain how a pH, an electronic pH system measures pH. You know, explain the principle behind it. You should be able to explain this page. All right. So I don't know if there are blanks on this one, But this just basically says exactly what I said earlier, just in another way. So I'm going to continue. These are a couple of drawings, diagrams that show basically how it works. You have the pH sensor and you have a reference sensor, and the reference sensor is actually contained, sealed, so you have no access to it. You cannot change the solution or whatever. And as I mentioned, it just puts out a constant voltage, a millivoltage, based on the solution. Inside the pH sensor will be a neutral solution, so it will have if there's a range of voltage, it will have, darn, I don't have a touch screen on my laptop. I was going to draw. It will have a, if this is the low end, it'll be in the middle. So an absence or an addition of hydrogen ions will lower the voltage beyond its reference point or raise it. And that's it. It's just compared to the reference electrode, reference sensor. Basically, it's just a voltmeter between the two. That's it. It just it reads this voltage, and then the transmitter will send out to the SCADA system or whatever's monitoring it, the transmitter, and it will just say the pH is this based on that voltage. Alternative methods, trying to remember from my chemistry, is it phthalate? I can't even say it. You chem people, phthalate, whatever. So there are, okay, you say it then. Unmute your mic. I could barely say my name half the time. Okay. Good. All right. Anyways, so indicators, they change based on the pH. Quite often used in swimming pools, that sort of stuff, hot tubs. I have seen them in industry as a quick and dirty check and backup check. Sometimes if an instrument fails or you want to just see if it's reading right, this works well, rather than do a full calibration. Okay. Also colorimeters. Everybody should know how. Oh, Frank did bad. He misspelled colorimeter. It's COLOUR, colorimeter. Okay, so obviously you grab the appropriate pillow pack, fill the vial up to the level indicated, and as per the instructions on the pillow packs, so if it's 10 mil, etc., drop it in, read. Calibrate these usually, it really depends based on use. I once a day. It's quick calibration. So, and you may, if there's been a few hours between readings, you may want to just give it a quick calibration. Temperature and buffers. Obviously, temperature does matter with pH. So buffers and solutions must be temperature compensated, right? So when calibrating pH instruments. So most pH instruments do have a temperature sensor inside, and they will automatically compensate for the temperature. So you don't have to, we don't have to look up tables and stuff like that. Can my timekeeper yell at me? Sound an alarm. Maybe 15 minutes before class ends. Yeah, or softly though. Okay, obviously pH instruments must be calibrated. In the pharmaceutical industry, they do a 5-point calibration. And that's typical, just because they have to be deadly accurate. In many laboratories, they also will do a 5-point calibration. I've never done one. The common calibration for pH instruments is a 3-point calibration. They should be calibrated fairly regularly. Again, you just follow your standard operating procedures or the manual. Cleaning the bulbs. Sometimes they will, over time, they will get clogged up with deleterious materials, whatever is inside the liquid. And so you have to just take a very, very soft brush and just lightly with soap, just clean it. If you have to store the probes for any amount of time, store them in a buffer solution of about 4 pH. And that's what we do actually at the college. I just actually splash a little bit of vinegar inside a solution or water, check the pH, and store them in there between labs. All pH instruments have a finite life. It really depends on usage. It's usually about a year, but sometimes it's less, sometimes it's more. Again, SOPs, and you have to constantly check with the standards, calibrate, all that sort of stuff. As soon as you start drifting, toss it. They're one use kind of thing. And that's it for page. Oh no, actually, there is one other thing. Can you guys write in for the 3-point calibration, the standards, and they have to be industry standard solutions. They cannot be made in-house or anything like that. So they're quite expensive. The industry standard solutions are Frank, are 4, 7, and 10. Having a brain fart there for a second. So a pH of 4, 7, and 10. So that's what we use in our industry. Usually is a 3-point calibration using standards of 4, 7, and 10. Good. So that's a big one. Everybody should know that. Any questions? Awesome. We're just whipping through. You know why we're whipping through? Because you guys don't have to look at me, and I don't have to explain why I didn't bother shaving or brushing my hair or, well, no, luckily nothing like that too much. No, I don't have board work or demonstrations to do. We will be doing that later on with videos. And that's why I want somebody to yell, the timekeeper, just to give me a 15-minute warning before the class ends. All right, so process control. The goal of all instrumentation is to obviously control a process. And quickly, I want somebody to either unmute their mic or type really quickly. What is the definition of process control? Let's see who's my favorite. Who can answer that first? Nobody's my favorite. Okay, there you go. Quinn is my favorite, as usual. Yeah, process control is controlling process. Keep it simple. So that's the ultimate point of instrumentation and why you guys have learned SCAPs and all this. And so this is an introduction to process control. You will have a full semester of process control, assuming you go into the water wastewater side. Right. Big quiz next Friday ish. You know, I'll let you know. Okay. So for this one, define process control. Examples, process control. Benefits of process control. So you should know, you should be able to list off like 8 of them on an exam or whatever. Examples of how process control is used in wet. Basics of P&ID, which we already went through before, and PFDs, process flow diagrams, and terms, concepts, process control. So these are basically the definitions of process control. This is the proper definitions, the engineering kind, but this is what I want. It is the control of a process. Actually, I think I got the student one open. 1 second, please. The control of a process, you know that already, Ron. You're just testing me, aren't you? Darn people. You know what? I don't think I have Alzheimer's. What were we talking about? Control of a process. Oh, it's the same bloody one. Oh, no, this is good. Okay, good. So obviously controlling a process requires observing something, whatever it is, comparing it to a desired value, and changing that parameter, adjusting it. So that is SCAPS in a nutshell. Mashed potatoes, you're making me hungry. Stop that. Okay, so anyways, that's the one thing in class. Really, when people talking, it is quite distracting. Here, chatting is also distracting. I'll ignore the chats. Okay, anyways, so think of, and I'm going to fast forward for a very quick second to our favorite here. Think about it. This is exactly what we talked about. It is observing some process. It is comparing it to the desired process, and then it is making that process match. That's all, you know, in a nutshell. This is the basis. People get PhDs in process control, but it's that simple. You know, keep it simple. So so obviously the world uses process control. You know, homeostasis, prey predator, that sort of stuff. It's a natural system, and we have adapted it to our industries in our lives. We use process control everywhere, including the water, wastewater technologies. So process control, basically, key feature for process control is having a feedback. So for instance, when we started this lecture, you guys were not giving me any feedback whatsoever except for raising your hands. That's it. It was really annoying. Nobody would talk to me and everything. And that's because I had disabled the feedback. You know, I did not allow you guys to have a voice in whatever. So key feature for, of course, all these systems is you know, having some kind of feedback, some kind of instrument to measure, and that way you know whether you need to adjust your process. So automatic process control came about widely you know, in the during the Industrial Revolution. That's when it really came, and it's continued since now. This might show up on exam. I've never asked it before, but you know what? Why not? This is an open book exam. So know the root of automation. Auto self, metals moving. These are just some examples of early, and these are some of the earliest ones I found for automatic process control. So fantail, windmills actually swivel. So if you have air blowing in this direction, that will turn this main fan. That's good. But if you've got air coming on the side here, it's not going to spin the fan. So what the fantail does is the wind hits this and it will turn this little fantail, and this is connected to gears, which will cause this whole top to turn, allowing the wind, the blades to meet the wind. See, this fantail will stop once it's parallel with the wind, and so this will always constantly face the wind. Another one is the centrifugal governor. And so for steam engines, as the speed increases, these balls will move out. They'll fling out, causing a valve to close a bit, which will, of course, decrease the speed, which means the balls will move back in, which will open the valve. And if tuned finely enough, you'll get a constant speed. Water level flow regulator, you know, or toilets is an example. So obviously we're mostly interested in automatic process control. Incidentally, you guys probably know this from making PowerPoints, but if you notice my slide here is, you know, it's got click add text and all this sort of stuff, but normally you guys would not see it this way. You would see this, and it looks perfect, doesn't it? That nasty little writing on the bottom was gone. So, but whatever. So this is actually the wastewater or water treatment plant. Some of you guys may ultimately end up working there or whatever. All right, so reasons for automatic process control. Big one, well, is just the changing variability of, let's say, wastewater system. You get a massive rush around 6 in the morning when people are getting ready for work and all that sort of stuff. And then another big rush, maybe coffee break, lunchtime, around dinner, and then that's it. It's quiet. And you need to constantly adjust for, you know, changes in pH or in whatever. So it's vital, number one. It maximizes performance, safety, quality, minimizes cost. So a big way it minimizes cost is rather than have 5 people in a water treatment plant, just have one sitting there maybe once a day, you know, for 1 8-hour shift, and have everything else automated. Or at the most, you know, 2 shifts, day and afternoon, and let the SCADA system run. But that's also a disadvantage, obviously. You know, people are laid off. We'll get to advantages and disadvantages later. So performance, quality, automatic systems, they just work. Like I mentioned earlier, last semester, the SCADA systems don't show up drunk. Instruments don't get, well, they do get sick, but they don't, you know, like have to stay at home because their kids are sick or whatever. You know, they just work. So that's, you know, unfortunately, the way the world works is they would industries would pay $1 million to replace a person. And if they could, they would replace everybody. Luckily, your jobs are protected by law. You must have somebody ELCP certified in a water or wastewater treatment plant. Yeah, I'll let you guys read this. I've already gone through it. Hopefully there's no blanks. Let me know if there are. One of the things with manufacturing that you should be aware of, manufacturers make money by, if they produce a lot of items, they can sell more items. So their idea is to produce as many items as possible with as few costs, and therefore they get better profits. With facilities, water and wastewater facilities, you guys don't really give us anything. You just cost us money. Yeah, sure, you give us clean drinking water so we live, and yeah, you take care of our waste so we don't have to throw it on the streets and stuff. But really, you cost us money. So the way to save money, rather than produce a whole bunch of stuff like normal manufacturing, the way to save money is to reduce costs in chemicals and manpower to produce the same thing. And so automatic control is used for that. Yeah, maximize, I'll get the best use from buildings and the workforce. Okay, 3 key terms associated with any process control system. You will have, for a process, you're always going to have disturbances, changing the processes, and some manipulated variable to keep the process where you want it. So know these 3 terms. Process variable. The definition for process variable is what you are controlling. That's it. So right now, actually, I just noticed it now that I mentioned it. My heater's on and it's hot. I'm going to take a quick 1-minute break and shut off my heater. Perfect. So I've now shut off the heater, and ideally, the process variable, the temperature in my process, this room, will eventually drop. Jesus, now quiet too. Okay, process variable is sometimes called the controlled variable or measured variable. We use process variable, PV, in this class. So again, I'm going to fast forward just for a second. You guys remember this beautiful thing here? There's the PV, the process variable. Alrighty. Disturbances. Inside my room, there are windows, doors, all that sort of stuff. And obviously I'm losing the heat. That's why the heater was on. So every process will have disturbances. The universe is tending towards entropy. It just happens. And that's why we must constantly adjust to compensate for these disturbances. And again, on this one, disturbance. So rather than refer back and forth, maybe write this down or be aware of this. Okay, open loop control. The definition I want for that is this: a control system that doesn't have a feedback loop or doesn't have feedback. So I'm sure some people have had a significant partner or family member or known a friend or somebody, you're talking to them and you get nothing from them. Not a blink, not a smile, not a nod. no feedback whatsoever, and you're lost. You don't know. Well, that's the same with a control system. If there's no feedback, you don't know what's coming out and what the process variable is. So open loop is similar to, like I mentioned before, walking up to your bathtub, turning on the taps and walking away. Yeah, it's going to fill, but you don't know what level there is. And especially the old style where there wasn't the emergency drain, they would just overflow. Okay, so open loop control, know what that is. Manual loop, closed loop. I've never asked this on a test, but you know what? Darn it all. This is fair game now. Open book. Manual closed loop is paying some poor sucker to stand there and watch whatever process variable you want, whatever it's called controlled quantity, and adjust the actuator to correct the process, to match the process variable. So this is an example of a manual closed loop system. I'll let you read it. I don't believe there are any blanks on this. Again, I'll let you read it. It explains quite well how it works. Automatic closed loop feedback systems. Oops. The way they work is you will have some kind of sensor there. Generally, they are electronic sensors, but they can also be mechanical sensors. And actually, mechanical sensors are the most common types in the world. Just, you guys already know this. The reason is because of our toilets. Having closed loop feedback system, you will have a sensor, a controller, and an actuator. So, and also a set point. So, I hate that word, the acronym, but SCAPS. Set point, controller, actuator, process, and sensor. So know this. I mentioned at the start of the semester that this is going to be on every single exam you take from now until you're 85. Go in for an eye exam, they're going to throw this at you. Know it well. Know every little dot, whatever on it. I will try to trick you with this somehow. Don't be fooled on an exam. All right. Deep sigh. This is a blow-by-blow, in-depth description of how this works so that anybody who is confused will get it. I'm going to go over it quickly, but it just uses, the idea of a car. So if you're driving, obviously your set point is going to be, where you want to be on the road. Your process variable is your position on the road, whether it's where you want to be or not. If there's a difference, you're going to have an error. That error is going to be sent to your controller, which is your brain, which says, oh, no, I'm headed towards, that busload of nuns. I better correct my steering, which sends a signal to your actuators, which are your arms and steering wheel, to adjust the process variable. And your sensor, your eyes, will again look at the process variable, check this set point. Now you've overcorrected and you're headed toward that family of ducks, and etc. On and on. Any disturbances would be things like stop signs or curves in the roads, or that family of ducks decide to cross the road or whatever. So I'll let you guys read this. I don't think, yeah, don't think I need to go through much more. This is kind of neat. I'll let you guys read this too. This just compares SCAPs. It's written a slightly different way than what you're used to, and compares it to this house. So I'll let you guys look at that. Know this well, because this theory, basic theory, is the basis for all industries. You know, if I could spend 20 hours on this, I probably should, and I will next semester. But this is vital stuff. Right. Advantages, disadvantages. Advantages, they work. They just work well. And I mentioned before, they don't get sick. They don't, need holidays, all that sort of stuff. Very precise control. Disadvantages. If they're not set up, they will oscillate and become unworkable. There's always a time lag, so a difference from when you start adjusting your process to when it changes to when the sensor picks up the changes and sends it back to the controller. It's very hard to set up a perfect system. That's why there are PhDs out there, and you'll learn more next semester about it. And sometimes, depending on the setup, it doesn't work well. So know all these pros, cons. I'll let you guys read all this. Are there blanks here? Good. Again, I'm going to let you read all of this stuff. 40 there is. Okay, thank you. So I've already, that's why I was kind of whining earlier. I was going, I've already explained all this stuff in great detail. So this is your homework. Know where this is. 40. Okay, so I'm going to go on to 41. If I'm going too fast, put up your hand, please. Okay. Sensing elements, you should know them. They are the actual element inside the sensor. So a capacitive sensing element, you know about, or a strain gauge sensing element, or liquid-filled thermal sensing elements, as opposed to the instrument itself. You guys know what a transducer is for sure. You know what a transmitter is. It picks up what the sensing element is reading and then transmits it out to the SCADA system or something. Yeah, we're done at 120. Set point. Any blanks on these? Controllers? Final control element? Okay, good. Might have to stop now. Yeah, I'm probably going to end it now, men and women. But 12 minutes left. I'd like to show you one video here. It's always nice to end on a video. How many people have been getting their Netflix in now? Because I think, yes, I was going to recommend shut down Netflix, because YouTube has this unbelievable repository of all the instruments you ever want to know. And I recommend them to our school, laugh out loud. Okay, anyways, good. I just want to show you. Unfortunately, these are new, and we haven't really been able to play around with them too much. So this is an introduction to the turbidity meter, the Hackney 360. Those of you who have seen it in the lab, I'd still watch it. It's 7 minutes. Thrilling stuff. Hi, John. So there's no sound, you said? If you guys couldn't hear the video, was there anybody who could hear the video? Yeah, I might just do that. Obviously, there's no sense in sharing, but you guys can you guys can just search for it. So it is TU5 series turbidity meters, basic operations. That's your homework, guys. I will probably throw a question or two on the test for that. Just understand the idea behind the 360 view for turbidity meters. And that's it, people. That's all I got for you. I will be repeating this in about half an hour, so come on by for another exciting time if you guys want. Till then, see you guys later.